This will be a short review on rational functions where we're looking at vertical asymptotes and horizontal asymptotes. So suppose that we're given a function f of x, which is equal to a p of x divided by q of x. And furthermore, suppose there's no factors of p of x in common with factors of q of x. Then every zero of q of x corresponds to a vertical asymptote of a rational function. So for example, suppose we're given w of x is equal to our x minus 1 times our x plus 3 times x minus 5 divided by x plus 2 raised to the second times x minus 4. Then this function is going to have a vertical asymptote where when the denominator is equal to 0, so set the bottom equal to 0, and we'll get 0 is equal to an x plus 2 raised to the second times an x minus 4, which means we'll have a vertical asymptote at x is equal to a negative 2 and x is equal to 4. Now, much like polynomials, we can look at the multiplicity of a factor. So the multiplicity of the factor x plus 2 is given by this 2 here, and the multiplicity of our x minus 4 is given by 1 here. So our vertical asymptotes again, which is given by x is equal to a negative 2 and x is equal to 4, will have a multiplicity, respectively, of 2 and 1. Now the multiplicity of vertical asymptotes are very important because it's going to tell us two things in general. Number one, if we have a vertical asymptote with even multiplicity, then the graph near the vertical asymptote either approaches positive infinity on both sides or negative infinity on both sides. And again, near vertical asymptotes, our graph will either look like y is equal to 1 divided by x to the k, or it's going to look like y is equal to 1 divided by x to the k with a negative 1 up top, where we have that k is even in both of these cases. So the corresponding graphs will either look like this graph here, or it'll look like this graph here. Now, if we have a vertical asymptote with even multiplicity, odd multiplicity, then this is going to, near our vertical asymptote, will have the following behavior. Either the graph approaches negative infinity on the left and positive infinity on the right, or the graph approaches positive infinity on the left and negative infinity on the right. Another way to say this is that one side of our graph is going to negative infinity, the other side of our graph is going to positive infinity if we have odd multiplicity. And in this case, we have either our graph will look like y is equal to 1 divided by x to the k, or our graph will look like y is equal to 1 divided by x to the k, where we have a negative 1 up top. So in either case, our graph will either look like this over here, or our graph will look like this over here. Now let's go ahead and review horizontal asymptotes. So again, suppose we have a function f of x, which is equal to p of x divided by q of x. Then we have three cases. In case one, let's suppose we have the degree of p of x is equal to the degree of q of x. In case two, we have that the degree of p of x is equal to the degree of q of x plus 1. And finally, the last case, we have the degree of p of x is less than the degree of q of x. And let's also suppose that a to the p is the leading coefficient of p of x, and b of q is the leading coefficient of q of x. So in the first case where we have the degree of p of x is equal to the degree of q of x, this gives us that we have a horizontal asymptote at y is equal to AP divided by BQ. In the second case, when we have the degree of p of x is equal to the degree of q of x plus 1, we don't have a horizontal asymptote, so this is no horizontal asymptote. Instead, we have a slant asymptote. So let g of x be the function, the quotient of p of x divided by q of x, then our slant asymptote is given by y is equal to g of x. And finally, in case number 3, when the degree of p of x is less than the degree of q of x, we're given a horizontal asymptote at y is equal to 0. So let's find the horizontal asymptote of our function w again. And again, w is given by x minus 1 times x plus 3 times x minus 5 divided by our x plus 2 raised to the second times our x minus 4. So here we need to find the degree of the top. So the degree of our x minus 1 times our x plus 3 times our x minus 3. And to find this, all we need to do is multiply the leading term of each of these here. And we'll get that this is equal to x cubed plus something else here. So yeah, I wrote that a little strange. Let me go ahead and just say that. Again, we're still looking for the degree. So this is telling us the degree of this function should be equal to 3. And again, for the bottom, what we can do is we can just go ahead and multiply the leading term of each of these terms here. So we want to multiply x times another x times x here. So that tells us that the degree of our x plus 2 raised to the second times x minus 4 is also equal to 3. So this gives us that the degree of our top function, p of x, is equal to the degree of our bottom function, q of x. Therefore, we have a horizontal asymptote at y is equal to the leading coefficient of p of x, which is 1, divided by the leading coefficient of q of x, which is also 1. So we have a horizontal asymptote at y is equal to 1. Okay, so we have information about the horizontal asymptote and the vertical asymptote, and now we have everything that we need to do to sketch our graphs. So let's go ahead and sketch a picture of, again, w of x, which is equal to a x minus 1 times a x plus 3 times an x minus 5 divided by x plus 2 raised to the second times an x minus 4. And the only thing that we need to do now is we need to find the x-intercepts. So we have our x-intercepts here. And to find our x-intercepts, we set y is equal to 0 and solve. So we get 0 is equal to an x minus 1 times an x plus 3 times a x minus 5 divided by x plus 2 raised to the second times an x minus 4. Well, multiplying both sides by the denominator gives us a x minus 1 times a x plus 3 times a x minus 5. And so we have 0 is at x is equal to 1, negative 3, and 5. So the x-intercepts are going to be given by 1, 0, negative 3, 0, and 5, 0. And since we're here, let's also look at their multiplicities. Again, each of these terms have a power raised to the first, which tells us that each of these x-intercepts will have a multiplicity of 1. So let's go ahead and just rewrite everything we know about this function real fast. And I'm going to just go ahead and summarize this on the next page. And now that we have all this information, we can go ahead and sketch a picture of our graph. So here is our graph. First, let's go ahead and look at the x-intercepts. So we have one at negative 3, 0, one at 1, 0, another one at 5, 0. Then we'll sketch our vertical and horizontal asymptotes. So we have one at x is equal to negative 2. Then we have another one at x is equal to 4. and we have a horizontal asymptote at y is equal to 1. So now we want to go ahead and sketch a picture of our graph. So we know that the horizontal asymptote is more or less telling us what's occurring at negative infinity and positive infinity on our graph. So if we go from left to right, that means on the very left, our graph is very close to our horizontal asymptote, and it first hits the x-axis at our x-intercept. Since our x-intercept has odd multiplicity, our graph is going to cross, and it doesn't touch the x-intercept between this x-intercept and our vertical asymptote x is equal to -2, which means that it eventually has to just go down to negative infinity. Now, this vertical asymptote has even multiplicity, which means that both sides of this graph are going in the same direction. So the right-hand side is also going to negative infinity. Now, the next time our graph touches the x-axis is at this x-intercept. And again, it's going to cross this x-intercept because it has odd multiplicity. And it doesn't touch the x-axis until after our vertical asymptote x is equal to 4, which means that it's just going to go up to positive infinity. Now, this vertical asymptote has multiplicity 1, so that means that the graph error function is going to go in opposite directions at our vertical asymptote, which means that on the right-hand side, we're going off to negative infinity. And then our graph is going to hit the x-axis. And again, this has odd multiplicity, so it crosses. And it doesn't hit the x-axis ever again since there's no more x-intercepts. And eventually, our graph is going to tend to the horizontal asymptote. And so here is a sketch of our graph.